Suppose we try to calculate the following triple integral, right? So for this triple integral, you have the scenario that z is bounded between square root of x squared plus y squared and 2. Y is bounded between negative square root of 4 minus x squared and square root of 4 minus x squared, and x is bounded between negative 2 and 2. What does it look like? So let's take a look at a very rough sketch here. My z on top is bounded by 2, all right? This is z equals to 2. This is a plane. Nothing really complicated about it. And from below is bounded by square root of x squared plus y squared, which is going to be just this guy right here. All right, so we have this object down here. This is the object that we're looking at, right? Trying to see a nicer behavior of this object. So if I slice this, or if I look at the projection in xy plane, the slice is going to be just a circular form. I'm right, I'm going to have a disk down here. The disk. This is the projection in xy plane, which is just a disk. All right, okay. Disk. Okay, so how do I know what are the boundaries for this disk? What is the radius? What is r for this disk? I already know that z is equal to 2, and I know that it's bounded below by square root of x squared plus y squared. So if I set square root of x squared plus y squared equals to 2 to find the intersection between these two, I get x squared plus y squared equals to 4. All right, so this object, this disk, has a radius bounded between 0 and 2. What about my theta? Theta is bounded between 0 and 2 pi. So we can convert everything into cylindrical coordinate system. And note that your y below is bounded by negative square root of 4 minus x squared and above by square root of 4 minus x squared. So there is no restriction on your theta. That's the reason. So x becomes r cosine theta, y becomes r sine theta, and z is equal to just z, right? Very good. So this guy becomes the integral. Here we have our x, our y, and our z, which all needs to be converted into z, r, and theta. So we have a triple integral. This guy becomes r. This stays at 2. And here you have r squared cosine squared plus r squared sine squared, which is just r squared. This guy is r, dr, d theta, and dz. So dz, r, dr, d theta. R is bounded between 0 and 2, and theta is bounded between 0 to 2 pi. Very good. So this ugly looking integral became this nice looking integral into r, theta, and z. Okay. So this guy becomes, here we have integral 0 to 2 pi, integral 0 to 2, and here we have r times r, which is r cubed. So you get, here you have, let's just write down everything for you, r cubed, dz, dr, d theta, which is equal to, guys, the inner integral is with respect to z. This guy can be written outside. So this is integral 0 to 2 pi, integral 0 to 2, r cubed, and the integral of dz is equal to, here you have z. So remember that. We are not changing anything over here. So we get z, which is bounded between r and 2, dr, d theta. This guy becomes integral 0 to 2 pi, integral 0 to 2, r cubed, and here you have 2 minus r, dr, d theta. Very good. You should be asking, can I separate these? Can I use Fubini's theorem? Of course, why not? This guy becomes integral 0 to 2 pi d theta, and integral 0 to 2 r cubed r2 minus r dr. Very good. So this is just 2 pi. And then if you do the multiplication here, so let us write down everything now that we are writing everything down here. This is 2r cubed, which is 2 over 4 r to the 4 minus 1/5 r to the 5, 0 to 2. So this is 2 pi, and here you have a half, and you get 16 divided by 2 minus 32 divided by 5. And if you simplify the whole thing, it's going to be 16 pi over 5.